In Chapter 6 and in Chem Activity 4B, we're going to be talking about chemical reactions. In Chapter 6, we get introduced to a variety of different chemical reactions, most of which occur through a so-called heterolytic method, that is, 2 electrons at a time. Now, when we talk about an acid-base reaction where this is the base and this is the acid, what we're doing is we are making a new bond between a pair of electrons on the base and the proton, and we are breaking a bond between the proton and the acid. Okay, so one way to describe this, of course, would be to talk about the proton being transferred. The acid donates the proton, the base accepts the proton, leaving behind a conjugate acid conjugate base pair. But as organic chemists, we tend to focus on the electrons, that is, bonds and lone pairs of electrons and what bonds are made and broken. So we describe it as a pair of electrons from the base reaching out to grab the H+, and a pair of electrons that was making up the HA bond being left behind on the acid. In other words, this is more of a Lewis acid-base description, where the base is donating a pair of electrons and the proton is accepting a pair of electrons. Now, another thing that goes into talking about acid-base reactions is which way does the acid-base go? And back in a previous chapter, we talked about the stronger acid always goes to the weaker acid. But in fact, we didn't talk about why one would be a stronger acid and one would be a weaker acid. We did. But ultimately, every time you break a bond costs energy. So breaking a bond costs energy. It is an endothermic process. So if you draw the breaking a bond like so, it costs energy. It's going to be an endothermic process, or it's going to cost energy like so. On an energy graph, we go from the lower energy, AH, to a higher energy, A with its pair of electrons left behind, and an H+. By default, if H starts out neutral, of course, if the acid starts out neutral, the A minus going to have a minus charge at the end to balance the charges. And as we go up in energy, we see it's going to cost energy to break that bond. But the reason acid-base reactions can happen energetically is because there's also a bond made in the reaction. In the process of the reaction, we are making a new bond between B and H. So if you think of B here and H+ getting together, they're high energy. And after we make a bond between B and H, we reduce the energy. And this reaction will occur energetically if the amount of energy you get back from making the BH bond exceeds the amount of energy it takes to break the AH bond. So in other words, it takes energy to break a bond, you get energy back when you make a bond, and overall, if the net energy change is negative, that is, if you get a net exothermicity of that bond change, you get more energy out from making than you get from breaking, then the reaction will proceed. Okay, we know from general chemistry, of course, that total spontaneity of a reaction, delta G, is a function of both the heat energy, which is really what we're talking about when we make bonds, as well as the entropy. But in organic reactions like this one, where we start out with 2 particles and we end up with 2 particles, the entropy change is very, very small, so that the heat energy change from making and breaking bonds, the delta H, becomes the predominant factor. Okay, so let's take one of our classic acid-base reactions from general chemistry and analyze it energetically. First off, we have HCl. We call it a proton donor, but you can think of the H+ as an electron pair acceptor, a Lewis acid. And then we have NaOH, whose one lone pair of electrons is going to be the electron pair donor, the Lewis base. And in this reaction, the Lewis base reaches out, grabs onto the H+, so it donates a pair of electrons to make a new bond between H and OH, right there. Meanwhile, the HCl bond breaks, giving a pair of electrons to the chlorine. And we haven't written out that, in fact, there was an ionic attraction between sodium plus and oxygen minus to start with. And there's an ionic attraction between sodium plus and chloride minus at the end. And, of course, there's a few extra pairs of electrons on chlorine all along the way. But overall, we've described now the same proton transfer from acid-base chemistry in terms of electrons, donating a pair of electrons to make a new bond, and breaking a bond to donate a pair of electrons. Okay? We can also talk about this energetically. We can put a value on the amount of energy it takes to break the HCl bond and the amount of energy it is given off by making the HEO bond. We know that HCl plus NaOH is a very exothermic process, so overall we go from a higher energy to a lower energy point. This can be described by an energy graph, where energy is on the y-axis and reaction progress is on the x-axis. Everything on this side of the equation equates to this energy level, and everything on this side equates to this energy level. So overall, this tells us the HCl bond, the one that's broken and costs energy to break, is much weaker than the H2O bond, the energy that we get back out. So you have some energy that goes into breaking that one bond, a lot more energy that goes out to making the second new bond. The ionic interactions do not greatly affect this process, and overall you have a net exothermic process that would be indicated by delta H value that's less than 0 or negative. Okay? So the other thing to see about this reaction graph is that I've actually written a progress bar along it, because in fact this H doesn't just jump from the Cl over to the water. In fact, it goes through gradually. As the O starts to grab onto the H+, the Cl H bond starts to break, and as you do that, you can travel along the energy graph until you get to a high energy reorganization point, after which point everything is net exothermic to get to your exothermic process. And in Chapter 6, we generate these reaction diagrams. There's one hump, one hill, for every unique set of bond changes that takes place, and the description of these bond changes as written by individual steps of a reaction, of which there's only one step here, and the bond changes as indicated by the curved arrows that show us where the electron flow goes. That is called the reaction mechanism.